solution to EMC problems. Now we can look at module 5.2, that is second module in chapter 5. So in this module we will go through some of the principles involved in grounding or earthing. The single point grounding concept, multi-point grounding, segregation of the grounds, and some examples will be treated over here. So what is meant by ground? So in the US people tend to use grounding, whereas in British or in UK people tend to use earthing. So often you can find both terms in the literature and both has more or less similar meaning. If you are looking at lightning protection, there often grounding means a physical connection to earth or the soil, because you need to drain most of the lightning currents away from your building or the structure and safely away into the earth. But often in EMC you do not require a physical earth for grounding. So their grounding is more like a third conductor. For example, in a power system wiring, this third conductor is not supposed to carry any current except in the case of a fault. So this third conductor connects the conductive enclosures of equipment to a common point within the power system, and this is mainly for the safety reasons, for the safety of the people from electrical shock. So this is often called equipment ground or earth, equipment earth. Now ground plane in a PCB is a circuit common or circuit reference, and this is usually connected to the power supply reference and to the shielding enclosure of the equipment. Sometimes grounding is also meant as a very low impedance path used as a return path for signals. So you can find all these four variations of definition when we discuss about grounding. So from the context you will know what is being meant. So two different types of grounding are often introduced. One is single point grounding and other is multi-point grounding. For example, if you have a subsystem 1 and subsystem 2, they may have some connections between them, and during any fault the desired path that you would like is along this straight to the ground wire. You do not want fault currents to follow along the cables from system 2 to 1 and then from there to ground. So how do you ensure that all the currents are following straight to the ground, all the fault currents, not to the other system? So single point grounding can often achieve that. So here a illustration is given. You have subsystem 1, subsystem 2 and 3. So you have certain currents I1, I2 and I3 during fault going to the ground. Now what are the advantages of this type of a scheme? One scheme is obvious. In chapter 4, while talking about crosstalk or near field coupling, you might have come across common impedance coupling. When from different subsystems currents are sharing a common path, you have a resistive drop like voltage sag in a power line, and that will interfere with the other circuit. So that type of, there is no common impedance between these systems in the ground circuit. So you avoid common impedance coupling. That is one big advantage of single point grounding. But at the same time, if you want to bring your ground leads all the way to a single point, you often require long lines, because this may be physically large systems and you require long lines, and depending upon the frequencies involved for the fault currents, it may form transmission lines. And you have seen in chapter 1, while discussing about transmission lines, under certain conditions and certain frequencies, they can oscillate between high impedance and low impedance. The impedance of the transmission line is not constant. It can vary between high and low, and that can create a lot of problems. And also at really high frequencies, you have a lot of radiation, because this may be electrically long, and you can have a lot of radiation phase coming from these grounding leads. So, for this reason, single point grounding may not be best suited for higher frequencies. It is best suited for low frequencies. So, that is where most of the single point grounding will be done. Then there could be another danger also, especially during lightning strike and all. If this is too long lines, you can have a potential difference between these systems. So, you need to really think of bonding between them in those type of cases, using spark gaps or something like that. When we discuss about lightning protection, we will go through that. So, this you have seen previously, but it is again shown just to illustrate one problem that one might encounter with single point grounding or with the long ground leads. In this particular calculation, one equipment is grounded using two types of conductors, a 3-meter wire of 25 millimeters cross section and 1 meter wire of 60 millimeter cross section, and its impedance is calculated, and it is shown the resonance peaks and resonance lows. So, beyond around few tens of megahertz, already this becomes unusable. So, this we have seen before. Now, multi-point grounding. Some of the bad effects of single point grounding can be avoided by multi-point grounding. So, there the ground is a plane, not a single conductor. It is a plane or a closely packed grid, conducting grid, where you have several subsystems arranged and connected to those with extremely short leads. So, all the currents are going directly to the ground points, and these currents are you do not form any common impedance path between these currents, because there are so many paths it can follow, not a single path. So, the advantage is that you avoid many of the radiated interference problems from long leads, and common impedance coupling can be avoided. Disadvantage could be that if you have an external transients coming into the ground plane, then it can create some problems. Say for example, a fault current happening in some equipment outside of the system, and a huge current is following along the path, then you can have some common impedance coupling and all. But otherwise, this is quite suitable for high frequencies, grounding of high frequencies. Segregation of grounds. Here you can have several type of grounds. Say for example, signal grounds, which are very low level, You have noisy grounds from relays, motors, high power circuits, etc., where the currents are fluctuating. And you have hardware ground where normally you do not carry any current, but only under fault conditions. So, you segregate those grounds and connect only at a single point, because you do not want the noisy relays and motors contaminating your signals and creating problems over there by changing the reference of the signal ground. So, you connect all those things to this main ground only at a single point, again to reduce the danger of common impedance coupling. Now, in shielded cables, ground often appears as a third conductors. If you have a shielded cable along the close proximity of a reference, and if you have certain currents in it, you have seen in the theory for shielded cables that beyond certain cutoff frequency, almost all the currents will be returning via the shield, not via the ground. Even though shield is connected on both sides to the ground, most of the currents will be returning via the shield. So, this you can see from the principle of flux minimization, or pure mathematically you can have a circuit diagram like that and find out that most of the currents are returning through that. Say for example, let us say at very low frequency, that is frequencies below cutoff, all the currents will be returning via the ground, and above the cutoff frequency all the currents will be returning via the shield. Now, this is an equivalent diagram for this cable. So, LG is the generator wire, this middle wire is self inductance. LGS is mutual inductance between receptor wire and the shield, and LSH is the self inductance of the shield. So, there are three inductances involved, two self and one mutual, and the coupling is shown here. The shield is having some resistance, and this is the load RL. Now, if you write the loop equation, 0 equal to IS times j omega LSH. So, we are taking this shield loop plus RSH, then a source that is a series voltage source due to this mutual coupling. So, which will be opposing this original flux. So, it is minus Ig j omega LGS. So, this equation you have seen before. Now, manipulating, you can say that LGS is equal to LSH, because it is very tightly coupled system. So, LGS equals LSH, mutual inductance between the inner wire and the shield is same as shield self inductance. So, with that simplification, this term we can get that I0 by Ig, which is same as shielding factor, equal to 1 by j omega tau s, where tau s is shield inductance divided by shield resistance. So, this you will get. Now, you can have two conditions. This will be approximately equal to 1 if omega is far less than 1 by tau s. So, when this part is almost negligible, and this will be equal to 1 by j omega t s, or RSH by j omega LSH for omega far greater than 1 by tau s. So, this is for high frequencies. So, this is corresponding to frequency below cutoff, below RSH by 2 pi LSH. And this is above that. So, here you see how the ground is functioning. Cable shields and grounding. Often shielding can be used, cable shield can be used to prevent radiated emission from the shield, from the wires, signal wires. So, if you have a receptor conductor inside and a shield outside, and if there are no shield currents, then all the you have electric field and magnetic field penetrating outside the cable shield, because there is no current on the cable shield. So, this is just a bare conductor. So, it does not matter where you have a shield or not, as long as they are not connected anywhere, as long as the shield is not carrying current, it is not having any effect. But in the second case, the shield is connected to the ground at one point, then at least you are shorting out all the electric field and only the magnetic field is penetrating outside. Still there is no shield current. But in another case, both ends of the shield is connected. So, if you have a shielded wire like this, you are connecting both ends to the ground, then you have a circulating shield current. So, Is is not equal to 0. So, in that case, you are confining the magnetic field also to the inside of the shield. So, you are not letting out any magnetic field outside. So, shielding can be used to prevent radiated emission from cables. So, this is one of the reasons why shielding is provided to cables. So, this is two way. It can also prevent this inner circuit from being affected by external fields. Both sides it works. So, again we look at the cable shields and grounding. Shielding to reduce radiator susceptibility. So, this part is grounded. Instead of, to make sure that all the current is returning to the shield, you ground only on one side and you can connect this end to the shield. So, this may be more effective sometimes. This is no shield and this is shield above shield cutoff frequency. So, you can say that this is a very large area being presented for external fields. Now, you are presenting very small area. So, that way also you can see it. But sometimes if you have connection at both ends, it can create some problems. So, you cannot do mechanically connection, without thinking on both sides. So, one case is illustrated here. Suppose you have a amplifier or something where some signal is fed using a shielded cable. Because of some external noise, you can have a circulating current like this around the cable shield, and this will create a drop. You can imagine the shield circuit. You have a shield inductance and shield resistance. So, the current is coming through and going out like this. So, if you write this voltage drop equation, minus j omega the mutual inductance I s plus j omega shield inductance L s h, and this is R s I s. So, we have seen before that self inductance of shield is equal to the mutual inductance between the signal wire and the shield approximately. So, this will lead the input voltage to the amplifier as resistance drop times the noise current. So, sorry, this is the not resistance drop, it is the drop across the shield resistance times the shield current. So, this quantity RSIS, that is the drop. So, this noise voltage will be superimposed on the signal. So, RS is the shield resistance. So, preferably you need to avoid this connection in this case. So, there is no uniform way of applying certain principles. You have to really analyze the situation and see if a measure that you take to avoid EMC problems will worsen the situations or not. So, you have to think very intelligently. Now, another problem is illustrated here to show the importance of thinking through and rather than just apply mechanically some measures. For example, this is an amplifier amplifying a signal. So, in this case the heavy currents are flowing like that, then returning back to the transformer like this. So, the signal is amplified. So, it may look a perfect circuit, but it can create lot of problems because you have a common impedance here, this grounding, and when heavy currents are flowing it is creating common impedance, and this is the reference. So, you create a voltage drop across this, and this voltage drop is superimposed on the signal. So, your output will be completely destroyed. So, you need to remove these connections from here and maybe connect it somewhere here, so that you are away from the path of this current. So, then there is no common current between this and this point. So, all the currents are traced out here. You can have noise from the load also, that also will create a common impedance drop across this. Now, here the solution is affected. Now, in this particular way, even though there is a common impedance, there is no current flow through this, because all the noise currents and others are returned via this directly over here. So, you do not have any current flow through ZC or Z3 or Z2. So, in this way, by simple rearrangement of the connections to the ground, you can solve this common impedance coupling problem. So, that is end of module